I'm James Lucas, and I'll be speaking a little about our Neurips paper on Don't Blame the Elbow, a linear VAE perspective on posterior collapse. This is joint work with George, Roger, and Mohammed, completed within the Google Brain team in collaboration with the University of Toronto. Posterior collapse occurs when the variational distribution of a variational autoencoder closely matches the prior distribution for a number of latent dimensions. We hypothesize that this effect is in part due to the optimization landscape of VAEs. To test this, we analyze the loss landscape of linear VAEs and present a thorough empirical analysis of posterior collapse in nonlinear variational autoencoders. We consider a linear Gaussian factor model called probabilistic PCA, first presented by Tipping and Bishop. We use a normal prior on the latent code Z and assume a Gaussian observation model with a linear map from the latent code to the output space. Variational inference provides a general methodology to train probabilistic models. In this setting, we proved that a variational autoencoder with a linear encoder is sufficient to do exact inference. As is typical, we consider training these variational autoencoders using the evidence lower bound, or Elbo. Typically, PPCA is trained with the EM algorithm or gradient ascent on the negative log likelihood, which can be computed in closed form. Interestingly, posterior collapse appears as stationary point solutions of the negative log likelihood minimization, and it turns out that, roughly speaking, the size of the observation noise affects the stability of the collapsed stationary points, with smaller observation noise making it easier to learn relevant features instead of the collapsed solution. We proved that the linear VAE is able to recover the global optimum of PPCA, and surprisingly, the training with Elbo is as good as training with the true log marginal likelihood, in the sense that no spurious local maxima are introduced. Another surprising result is that, unlike PPCA, the linear VAE is fully identifiable and exactly recovers the principal component directions, not just their spanning subspace. In our paper, we validate our theoretical contributions in the linear setting and use this simple setting to explore other interesting features of VAE training. For example, understanding stochasticity in Elbo computation due to the reparameterization trick. We also provide a thorough empirical evaluation of nonlinear VAEs, where we discover that, as in the linear case, the observation noise has a strong influence on the degree of posterior collapse. However, unlike the linear case, we find that it is much more difficult to learn the correct noise model, meaning that ultimately the nonlinear VAEs typically do have collapsed posterior distributions as their final solution. For more information, please see the project website where we have public code available and our paper which is live on arXiv. Thank you for watching.